When we introduced parametric curves, one of the benefits we discussed was that we could trace any curve we wanted. We were no longer restricted to working with paths that were functions of the form y equals f of x. The step up to parametric surfaces is the same thing. The simplest example to think about is a sphere. If we tried to use z equals f of xy to capture the shape of a sphere, we would only be able to capture either the top half or the bottom half, but not both at the same time. We are still going to use vectors to locate points, just as we did with curves. But now we're going to have two input variables, which corresponds to the two dimensions that exist on the surface. We want to talk through the process of creating a parameterized surface. An instructive example is the torus. A torus is basically a donut-shaped region. How can we describe this shape using parametric equations? We first have to carefully define the shape. We will begin with a circle of radius a on the xz plane centered at the point b0. Then we will rotate this shape around the z-axis. We will first begin by getting parametric equations for the circle. We will use the variable t for this. This should be familiar with your previous work with parameterizing circles. We do need to make a couple changes since we are in the xz plane instead of the xy plane, and we've shifted the center away from the origin, but neither of these should be too complicated. We now need to think about how this shape is rotated around the z-axis. Rotation around the z-axis does not change the z-coordinate, so we will focus on just the x and y coordinates. Each point along the circle gives us a radius with respect to the z-axis. We'll call that radius r for now. If we want to take this point and rotate it around the z-axis, we would be tracing out a circle of radius r parallel to the xy plane at a fixed height of z. We know that the parametric formula for such a circle is r cosine s, r sine s, z, where we're using the parameter s because t has already been used earlier. The values r and z come from the first part, and so we just need to make the substitution from the original circle to get the final result. What does this vector formula mean? For every pair of values st, we get a point somewhere along the torus. And based on the construction, the s value gives us an angle when looking down the z-axis, and then the t value gives us the angle relative to the center of the tube. Activity 11.6.2 works through creating a parameterization of a sphere. This one is particularly important to work through because it lays the foundation for spherical coordinates, which we will discuss a couple sections from now. Just as we could parameterize curves based on functions, we can also parameterize surfaces based on functions. For curves of the form y equals f of x, our parameterization was t f of t. For surfaces of the form z equals f of xy, we use st f of st. The same warning applies to this as with parameterizing curves, in that you should not use the coordinate variables x and y as your parameters. Doing this creates confusion and can lead to problems down the line if you're not careful. Now that we have parameterized surfaces, we can try to do some calculus with them. Our goal will be to come up with a formula for the surface area of a parameterized surface. This derivation has a lot of steps and draws on a lot of ideas, so you may need to go through it a couple times. When we were looking at polar coordinates, we saw that we made a small polar rectangle when we made small changes to r and theta. When working with a general parameterization, we're going to get some other type of rectangle. Just as with polar rectangles, these aren't actually rectangles. They are some sort of warped shape, but we're going to refer to them as rectangles because there isn't a better word to use. You can see these rectangles on the images of the torus and the sphere from the book. Notice that towards the top of the sphere, the rectangles are getting quite warped. All of these rectangles come from drawing out curves of constant s and t. Again, we can think about polar coordinates as a model. The polar grid is nothing more than drawing curves of constant r and theta. We want to do the same thing with our general parameterization. So now we come down to the real meat of the problem. How do we calculate the area of one of these rectangles? Let's pick some ordered pair s0 t0 and imagine drawing a rectangle where we change the parameters by ds and dt. This rectangle is formed by the curves where s and t are constant, and we know that the sides can be labeled by these equations. This region can be roughly approximated by a parallelogram. The key insight is that the sides of the rectangles are curves of constant s and t, so that the tangent vectors can be used to give us their directions. But the tangent vector is only a direction and not the length of the vectors. To get the appropriate length, we can think of this using differentials. The partial derivative of r with respect to t gives us the vector tangent to the curve of constant s. It is the amount of change in position per unit change of t along the curve. So if we want to approximate the change in position moving along that rectangle, we would use partial r partial t multiplied by dt. That dt term accounts for the step size that we're taking in the t parameter. The same idea works in the s direction. And now we use the fact that the length of the cross product of two vectors gives us the area of the parallelogram spanned by those vectors to get our area element. We get ds is equal to the length of r sub s ds cross r sub t dt. Because of the properties of the cross product, we can factor out the ds and the dt, giving us this alternative representation. The book uses dA for ds dt, since ds dt acts just like dx dy would, but that notation can potentially get confusing if you're not careful, so I'm going to leave it like this. Then to get the total surface area, we integrate over all the small surface areas, and that gives us our final formula. Just as with the other section, once you have the formula, it's a matter of doing some practice calculations to get comfortable with it. All of the conceptual work is in the derivation, and the calculations are just time to practice. Pay attention to the limits and sketch out the region of integration if you need to.